Great. Okay, and I'll remind people if they have questions for the panelists to put them in the Q&A. We've heard a bunch of great talks this morning. We heard Heather Sagla talk about the various physics that goes on the surface of the sun and how that affects RV variability. We saw Annelise Mortier tell us about sun as a star observations, including a pretty jaw-dropping plot that I am sure we will talk about. We heard Jen Burt talk about the strategies, the practical strategies for solving a lot of these problems with stellar activity and other sources of RV jitter. And then we just heard Colin talk about telluric lines and how they mess up our ability even to measure all that stellar jitter. So also on this panel discussion, we have Peter Plodchon, who had a pre-recorded talk. And so I think I'll open with Peter and let him have 10 minutes to summarize the talk he has.
Okay, great. Thank you. Can you hear me okay?
Yes.
All right, well, I guess I need to get some slides up and share a screen real quick.
I guess we could go through an order if you'd like a minute. We can start with Heather instead. Why don't we do that? We'll start with Heather for 5 minutes with any slides she has, and we'll let Peter put his slides together. Sorry.
Okay.
That's easy because I don't have any slides. So Peter, you can kind of get yours up and ready as you go. I mean, for me, I would just stress that the sun and sun-like stars have a convective envelope. So there's heat transport by convection at the surface. And it's the interplay between that convection and the magnetic field that drives the physics of most of the various sources of stellar originating variability in our RVs.
All right. Annelise, would you like to give a summary of your talk, or do you have any additional items you'd like to cover?
I also don't have any slides. Just wanted to repeat that treating the sun as a star comes with its challenges because it's resolved in our sky, so it has observational issues. But once you do treat it as a star, it has amongst other things, confirmed that suppression of convective blue shift is the main source of RV variation for solar type stars. It has confirmed that it is still a mess, that it correlates only weakly with our traditional activity indicators, but that we now have superb data that is coming and will soon be available to all of you, that we can start to actually understand it. So I'm sure you all remember the very scary plot I showed of the blue wiggle and the black mess.
Great, thank you, Annelise. Jen Burt, do you have, would you like to summarize your talk, or do you have any additional slides to show?
Sure. Yes, I mean, the takeaway from my talk was mostly walking through different stellar activity indicators that we use to try and map what the star is doing. So things like the calcium H and K lines, H alpha, the calcium infrared triplet, and then different ways of trying to use the information gleaned from those lines to help better model the RV signatures in the star using things like Gaussian processes or moving average approaches. The one thing, this came up in a couple of questions that I didn't talk about, was how do we identify new stellar activity indicators as we push into new regions of wavelength space with near infrared spectrographs, or even in the traditional visible part if we want something beyond just calcium. And so I would advise everyone to go look at Alex Wise has a paper on this topic from 2018, where he looks at a variety of HARP spectra and looks for lines that show correlations with the S-index lines, and does a variety of other more detailed analyses than that. But in general, right now we tend to bootstrap back to an indicator that we know well, like calcium, but he uses this as a way to identify potential new lines that are a little further into the visible, away from the blue part of the spectrum, which might be useful in the future.
Great, thanks, Jen. Colin, we just heard from you, but perhaps you have some a quick summary or additional slides you didn't have time to get to.
Yeah, just a quick summary. So in my talk, I was kind of summarizing the issue of telluric absorption features, and then going over some ideas of how we could try to deal with these things. And then talking about how down the road, I think there are a lot of great avenues open to us to sort of solve this problem as far as EPRVs over the next generation of instruments, at least. I don't really have anything else to add. I'm happy to cede my time to Peter.
All right. Peter, will you tell us about your pre-recorded
Yeah,
talk?
I'm going to go ahead and share my screen. So you should be looking at my screen now, if you can just confirm real quick.
Yes, we are.
Yeah, so I have a pre-recorded talk, and I definitely won't be using 10 minutes. I hope not, anyway. I am the PI of the Earthfinder mission concept study. This was selected by NASA during a call for proposals for probe mission concepts. And the goal of Earthfinder, the study itself, was to provide input to the 2020 Astrophysics Decadal Survey. The goal of Earthfinder is to basically do for radial velocities what Kepler did for photometry, which is bring about a new era of precise spectroscopy at high resolution and really take a good look at what would we be able to do with such a mission in space in the future. And this report is available on the archive, and you can watch more in the pre-recorded talk. There's a large team of over 50 scientists around the world that participated in this mission concept that we carried out from the proposal period all the way up through the study. Lasted about 3 years worth of work. Next slide. Okay, so Earthfinder can be summarized up in 4 words: radial velocities in space. And the focus of the study and the focus of my pre-recorded talk are what are the key advantages that you might have with regards to mitigating tellurics, the absence of Earth's atmosphere, and in particular, what advantages would it have with mitigating stellar activity. And the goal of the space-based mission would be to take the Kepler spacecraft and replace the instrument bay. And it would have a 1.5 meter aperture, the same as the Kepler telescope aperture. So a lot of flight hardware heritage to draw upon. And with that kind of aperture, you could do a continuous survey of about 50 or so bright nearby FGK main sequence stars that, say, a future flagship direct imaging mission would target. We'd put it in an Earth trailing L2 orbit, and it would have essentially 3 arms of a spectrometer covering the visible all the way out to 2.4 microns in the near infrared. And you could read more and see in my pre-recorded talk as to why having those additional wavelengths would be useful for mitigating stellar activity, or potentially useful anyway, as well as a UV arm for chromospheric activity indicators at 2 different wavelengths, allowing us to probe 2 different scale heights in the chromosphere of stars. Whereas from the ground, we primarily can only do 1 chromospheric activity indicator. As mentioned, no telluric atmospheric effects, which we heard a lot about from Colin in the last talk. Those all go to 0. And because we'd be in space, we'd have a diffraction limited beam, and that would allow us to use a single mode fiber-based spectrograph, which allows us to have theoretically the most compact spectrograph, and thus also allow us to go to higher resolutions, which, as we've heard yesterday and today, would be useful for potentially mitigating stellar activity, as well as providing chromatic, the largest possible wavelength range from the blue visible all the way out to the 2.4 microns in the near infrared for looking at radial velocity color. I think one of the important outcomes of this study is that radial velocity color, in other words, you take a measurement in the visible and take a measurement in the near infrared and subtract it, is the only technique that perfectly subtracts off the planet signal and isolates the activity signal. Now, in this case, the activity signal is chromatic, and so you still have to do some modeling to get back to what component of the visible or near infrared channel radial velocities are due to activity. And we put it in the L2 orbit for thermal stability, and so on and so forth. And there's a schematic here on the right showing the instrument package in the bottom right. In the upper right, you might assume that you could look everywhere, including away from the sun. But if you point directly away from the sun in space, you end up heating the satellite bus, and that creates a thermal gradient across the instrument bay. So there's actually an anti-sun avoidance zone in addition to the sun avoidance zone. But we were able to, with some small modifications to the Kepler spacecraft design, basically achieve a continuous viewing zone and instantaneous viewing zone of roughly 70% of the sky. And one of the things you cannot do at all from the ground, thanks to weather and the sun, is achieve uniform random cadence, which will allow you to mitigate any type of aliases that get introduced. And you can watch and learn more about that in the pre-recorded talk or read about it in the talk. We also simulated a relatively realistic survey of a set of 63 HABEX targets and did planet injection of multi-planet systems and recovery tests with Radial, and showed that yes, basically this mission could recover Earth analog signals under the assumption of stellar activity mitigation, which of course is a big assumption. But there are a number of key advantages to that. You know, if we're looking for habitable zone planets on 1 to 2 year orbital periods, and we have this seasonal alias on the ground, that's an alias in our analysis that's hard to get around. But in space, you'd replace that with 2 6-month visibility windows, which would completely alter the aliases in searching for habitable zone analog signals. And in addition, there's a huge number of science cases, astroseismology, direct spectroscopy of exoplanets, water in the local universe, a UV space capability post Hubble, and more. And I think that's all I wanted to say. I would say, to conclude, we did do a comparison survey of Earthfinder compared to the cadence you could achieve on the ground with an 8-meter class telescope with 25% time. And Earthfinder actually outperforms a 25% time on an 8-meter in achieved cadence in terms of number of observations per star for the same sample. And you might go, how is that possible with the ratio of aperture diameters? And the answer comes down to a few factors. Your throughput efficiency is much better with a diffraction limited spectrometer in space. You have more spectral grasp, and in particular, no daytime and no weather. The daytime and weather losses get made up from space. So rather than thinking about it as like a 1.5-meter telescope on the ground, think of it more like a 5-meter telescope on the ground. That's kind of the effective number of seconds and area available by having a 1.5-meter in space. And so with that, I'll stop. Thank you.
Great, thanks, Peter. That's really cool. Well, I want to kick things off with the figure that Annalise showed, that showed the solar radial velocities measured at HARPS over many years. It seemed to track the solar activity cycle. And you said a lot of people would be surprised by that. I'm sure Heather has a good reaction to that, and I want to get to that. The reason I'm so interested in it is that when years ago, I thought I had discovered the first good Jupiter analog. We were a little concerned because the star that we were observing had an activity cycle of 10 years, and we had detected a 12-meter a second, 10-year signal that looked just like you would expect Jupiter to look around the sun. And so we had some concern it was an activity cycle, but we decided it couldn't be because lots of stars have activity cycles, and this was the first one that had shown such a signal. It looks a lot like that plot of what the sun is apparently doing. So, so my question is to the panel is, why don't all stars show such a strong correlation with activity cycle, all cycling stars? Why does it seem to be only a few stars like the sun and maybe the one I observed that do that? You don't have to answer definitively. I'm just curious what your thoughts are.
It's a great question. Well, for one thing, the calibration jump issue in both HARPS and HARPS North will not just have affected the sun. It will have affected all our stars. So the entire database is being re-reduced. And we do see in some of our standard stars that the long-term behavior has changed. So I don't know whether we killed your planet. So there is a possibility that these long-term effects are, could have been instrumental because of simple aging of the instruments and the calibration lamps. But why we do see signs of activity cycles in several stars. I think there's a poster right now on Slack about it, and I've seen other papers about it. We do see for several of our stars that we have a long term for, in general, it tends to very well relate with the S index or RHK, pick your favorite flavor. As we see now for the sun, that if there's one thing that the RHK and the S index tracks well, it's the general magnetic cycle. So if they both show the same behavior, then obviously your RV variation would be from that. But for any long-term signal, you do run the issue that there's a long-term effects from the instrument itself that you're not taking into account. The same happens with full width half max, for example, that can broaden over time because of your instrument getting slightly worse over time. That creates a long-term effect.
Got it.
Heather,
what did you, oh, go ahead, Colin.
Oh, I was going to ask a follow-up question, but I'll Heather go first.
Heather, what did you like about that plot?
I like that there's just a lot more going on from the sun. So originally we think that there's quite a lot of variability going on, especially on that rotation period side of things. And we kind of have an idea about what the sun is doing over an activity cycle because we can track the spots and the intensity variations or the brightness or whatever. But to really see the big difference about how much just your data reduction can improve things, that's like the really incredible thing. So we haven't changed the instrument in this case. We changed the way that we analyzed the data. And so in some sense, there are ways where we can get more information out of the same content. And I think the same is going to happen when it comes to just our analysis software when we're trying to disentangle stellar variability, is that there are sometimes we can tease out more information than we originally thought. I mean, the radial velocities that we're looking at come from thousands of lines. So there's a whole host of information there. And I'm really excited to see what's going to happen when we start reanalyzing these correlations now that we have the new pipeline and see, like, okay, now does this magnetic flux track even better the radial velocity shifts that we see? And hopefully it will really help us fine tune the activity indicators that we are using. And especially when we apply it to the whole stellar database of the HARPS and HARPS North, and it'll help us track and see how are these activity indicators that Annalise and Jen talked about, how are they manifesting in other stars, especially when you have these subtle effects where just the data reduction can make a huge difference.
Can I riff on that for a second? I think that's a great point, Heather. I mean, much of the radial velocity community for the first 25 years of its existence made the assumption that the spectrum of a star is static, and it's not. And there are subtle temperature changes and abundance changes from activity, and moving more towards a dynamic spectra assumption in all the lines, I think is the way forward. And we saw some work on that from Vinesh Raj Paul, where he's cross-correlating every observation with every other observation, kind of a data-driven approach to the assumption of the star is no longer static. But I think there's a lot more we can do. And I know people like Javier and yourself and others have, did custom line masks for lines that are more sensitive to activity versus others. But really breaking away from the 25 years of kind of inertia that the cross-correlation technique and the follow-forward modeling technique have relied upon, that the spectrum of the star, not just a spectrum is static, not just in line shape, but in flux as well.
Peter, that gets actually into one of the other questions I was going to ask, which is about the idea of purely empirical approaches, or at least leveraging, in addition to these physics-based approaches we've heard so much about, more empirical approaches to all of these problems. So instead of thinking about, oh, this is a line, I understand that it's activity sensitive, just empirically asking, how has the spectrum changed? Look at stars that are active and say, what is different about those spectra? Maybe some sort of machine learning approach that then can extract RV variations due to things other than center of mass variations, but also perhaps for work with telluric lines as well. We know the high trend database isn't complete. How much of all of this can we do purely empirically, and how much would that help?
Well, I guess you're directing that to me, but and the whole panel in general. I mean, just from experience of the past 25 years, the answer often ends up being both, right? There are physics approaches and purely empirical approaches go hand in hand, and people push on both at the same time, and we make different advances. And Gaussian processes, to some extent, is a data-driven approach. There are some physically informed parts of that, like the rotation period and the spotlight time. I see what anyone else has to add to that, but I think we need to do both.
Yeah, I would definitely second that. Annalise, did you want to jump in? Okay, I would definitely second what Peter is saying there, that we really need to combine both, because there's sort of caution on both sides of the things. If you have a purely data-driven technique, you may not be understanding the physics, so you might not actually understand the signal that you're looking at. And if you are just sort of taking a purely empirical approach and sort of, one example is just blindly binning things and doing it until you get a lower RMS, you can then be missing out on signals that are actually present in the data. And some of that happens also with these machine learning things and Gaussian process, whatever. You can eat other signals and stuff. So it's important to understand what signals your data-driven things are actually identifying. And then that's where the physics comes into play. And that can't just be purely simulation, because we need to validate those empirically as well, because if you got your input model wrong, then your output model is going to be wrong. And that's, again, where we can kind of look to the sun, where we can really validate both of those. And then also for particular stars, it's important to make sure we're really validating that both on the sun, where it's our nicest test bed, as well as towards other spectral types.
And this has been an area,
sorry. No,
it's
Jennifer.
been an area where for the EPRV initiative that Heather mentioned and that Scott's going to give a talk on tomorrow, I believe, there's been a big emphasis on trying to build stronger collaborations with heliophysicists, with people who have been studying the sun for decades, because I think one of the things we need to do going forward is start paying attention to the differences in the absorption lines. We tend to treat them all as kind of the same thing in a spectrum of the star, but those lines form at different depths and at different pressures. They reflect different parts of what the star is doing and different types of variability that they're sensitive to. And that's at the moment not something that is addressed very well by RV approaches and measuring like general cross correlation functions for stars. And so moving forward, I can imagine more detailed data approaches that treat different types of lines, as independent groups, but that data analysis approach has to be informed by the physics of where do these lines come from, how do they form, what are they telling us about the star.
If I can give perhaps a more basic example, people often treat an activity signal, they label it an activity signal if it's unstable over time, and a planet signal if it's stable over time. Now, obviously, that depends on the time span of your data. And for very cool stars, some of these active regions do live for very long times, and the activity signals created by that can have the appearance of being stable over the time span that you took your data, but are not actually from a planet. So if you don't take into account the physics of knowing that cool dwarfs, active regions live longer and are stabler than the ones for G dwarfs, for example, you might totally miss that if you just use a data-driven approach.
And one other thing is that sometimes you can improve the efficiency of your observation strategy as well if you take into account the physics. One example is something like pressure mode oscillations. So if you take into effect the fact that we know that these are tied to the mass and the effective temperature and the surface gravity, then we can fine tune our observations to those physical parameters and be more efficient. And that's just sort of one example there.
Colin and Peter, is there any advantage to this from the telluric perspective? How much do we need to rely on high trend, and how much can we do empirically?
So I would say that when it comes to tellurics, this is actually a place where data-driven models are super promising. I would say in large part just because it is a highly constrained problem. So, again, throughout the optical down to line depths of much less than 1%, HiTran is basically complete and accurate. So, for example, in a big analysis of FTS spectra of the sun, there was only like one of many thousands of water lines that was not correct in HiTran. So we have excellent physically informed starting guesses, right, for our data-driven models. But then also what Earth's atmosphere can do is also super highly constrained, right? A few model parameters can probably do a very good job of describing what Earth's atmosphere is up to at any given time. So yeah, I think that, there's definitely I'm sure that there's some empirical data that could be gathered that could really help us with our modeling of telluric data. But it's kind of neat that right there in our spectra, in the limit where you have a lot of spectra over a wide barycentric throw, there's probably the information you need to do a pretty good job of solving this problem. Unless the lines are eating all your photons, then it's hopeless. Then you have to go to space.
By the way, can I have about $1 billion? Anybody got some loose change around?
PayPal work for $1 billion?
So one thing that I found really interesting about Xavier's work identifying that Gaussian of lines, some of which misbehave, and on the red and the side and the blue ones in the middle that seem to behave well, was not just that he could identify which lines are well behaved and we should trust for radial velocities, but I think equally valuable is knowing which lines are sensitive to RV jitter, and not thinking of them as bad lines, but thinking of them as diagnostic lines, and isolating them and saying, when that line varies, you need to start being suspicious. And so not throwing that data away, but thinking of some sort of regression or continuum of diagnostic lines to good lines. Does this, do people think this idea has merit?
Yeah, I think something that came up in the Q&A text questions was, how do you decide when you should be adding a component to your model that addresses stellar activity? Because people are worried about overfitting things or adding, model components that aren't required. And so traditionally that has been done by looking at, things like the photometry or the calcium lines or the H alpha lines. And if those show variability in a structured way, like, you should try to address that. But the more diagnostics we have, the more lines we know to look at and say, if these are showing correlated structure, then we should be worried. I think that only benefits us, because I think it is important to make sure that additional model components you add are physically motivated or are motivated by something you're seeing in the data, and you're not just throwing them in from the beginning because it might help to shrink your error bars or shrink, the RMS of your data by a little bit.
Yeah, I think it's a very simple concept. You should use all the information that you have available. It's the same with telluric lines. Masking them out in the optical is quite easy. If you start doing that in the near infrared, you throw almost your entire spectrum away. It's just co-modeling it will always give you better information. And the same is true for all the stellar lines. If you use them as specific individual lines rather than treat them all as the same Gaussian, which we already know is not true, then you'll just learn from that much more than the approach we are having now. So I think many people are working on the concept that we should use the entire spectrum and sort of step away from averaging in that one blurred CCF that you then fit with a Gaussian, whilst you know that it intrinsically is asymmetric.
Yeah, adding to that, just echoing what has been said, really, but also adding that there's also some really interesting work from Andrew Thompson and from Alex Wise, where they're taking the active spectrums and dividing by the sort of inactive spectrums to identify these lines that vary. And what's interesting about those is once you find the lines, whether you do it by the Demusk approach or by these approaches, Because then you can, again, tie them back to the physics and be like, okay, are these lines varying because they're temperature sensitive or because they're magnetic sensitive or they're sensitive to the excitation potential? There's a lot of physics embedded into it. And so we want to understand why they're varying, and then we can tie those back in, because I absolutely agree that we want to be using these active lines as diagnostics so that we can really understand them. And we want to know how those active lines are impacting the whole spectrum that we use to measure our precise radial velocities as well. So a composite approach is awesome.
Yeah, thanks for plugging Alex's WISE work. There's a plot in the Earthfinder report specifically looking at the correlation with activity and the actual kind of potential energy of the individual lines, how they form, you know, what quantum transition. Every one of these lines has a specific energy transition associated with it and a specific specific atom. The other thing I'd say is we've talked about data-driven approaches and we've talked about physics-motivated approaches. I think there's a third pillar to that, which is, of course, the instrumentation. And you know, all the work that Annelies has done is really incredible, seeing these correlations emerge in 70 centimeter per second signals, or the instrumentation noise or the photon noise is at 70 centimeters per second. We're in store for another revolution with the new generation of spectrometers coming online that are going to make I mean, we worked really hard to tease those signals out of the solar data, and they're probably going to be at much higher signal noise in the next generation of instruments coming online. That's really exciting to be able to do that and really break apart and tease apart more of these effects.
Okay, I want to get back to this idea that that not all stars are the same. And again, the one I keep thinking about is cycling stars. We have a star like Sigma Draconis 185144, which is at Keck High-Res, one of the most stable stars, which has a huge activity cycle, but that we cannot see in the radial velocities. And so I have this concern that the nature of RV jitter might be different in important ways between two stars that otherwise look identical. And so I wanted to ask Jen in particular, is this something you see? Like, I find that I'm always surprised by which stars turn out to be the absolute quietest when there are stars that seem to be just like them that are just not all that RV quiet. How do you interpret that?
Yeah, that's definitely a thing we've seen in like the Carnegie surveys that have happened, and especially in doing follow-up of test planets nowadays, like stars that have very similar photometric light curves. And you think, oh, well, we got a great RV measurement of this planet, and so this star looks exactly the same, so it'll all work out nicely again, and that is not the case. A thing that I have come to appreciate more since being at JPL and working with Eric Mamajek is that you need to pay more attention to the star. I think there are a fair number of RV papers, especially earlier, you know, a decade or two ago now, where the description of the star in a given paper is kind of like, here's the photometry and here's the, you know, basic mass and effective temperature we used. And then, you know, people only care about the star in the context of getting a planet mass. And what we're learning now is that you need to pay much more attention to what the star is doing. You need to look into things like, are there any measurements of the star's magnetic activity or XUV flux, or, you know, better age constraints that tell you something about where it is in its evolution and what that might tell you about its rotation period, because those spin down over time. And so I think, you know, starting to look at stars on additional axes, on comparing how stars behave, not just in terms of effective temperature and mass, but in terms of, you know, age and metallicity and measurements across a whole spectrum of different instruments is, you know, would help us to have a more comprehensive look at things. Because yeah, at the moment, I don't know what the best indicators are. You know, yes, an S value gives you an estimate of how active the star is, but we've also seen recently that, oh shoot, I'm forgetting the name of this survey. Maybe someone can help. But you know, for a long time, we avoided stars that had R'(HK) measurements that suggested they were a little bit active. And there was a survey that was done recently where people focused on exactly the stars that looked like they had excess R'(HK) measurements. And that was actually due, I think, to like dust around the stars that was an indicator that there are planets there. And like that has been quite successful. Of the stars they've targeted, which we traditionally would have avoided for being too active, they found a fair number of planets so far. And so yeah, I think better characterization of the star across a number of axes is crucial for moving forward and being able to actually predict which stars are likely to be problematic for intensive RV campaigns.
I think the
Do we have-
additional problem with activity on stars is, like, suppose you're an alien and you're observing the sun right now. You would think, oh, cool, I found myself a stable star because the sun right now is actually quite stable. If you would have looked 7 years ago, or if you will look in 7 years, you might make a completely different conclusion, because at that point, the scatter was quite large because it was at the top of its magnetic cycle. So the problem that we often face is that two stars may look the same, but if there are completely different points in their magnetic cycle, the RVs will behave completely differently if you're observing them at this point. So a magnetic cycle is really long, and you have to take that into account, that you go through that cycle. And even for the same stars, if it's then offsetted, you might hit a lucky shot, or you might be very unlucky.
I dream of the day where radial velocities can tell us the inclination of the star, its spin axis. You could take the same star, identical stars at two different inclinations, and you'll have two different activity signatures.
Can you be a little more specific about that?
Sorry, Jason, what was it?
I was asking Peter if he could be a little more specific about what he means.
Okay, so on the sky, the star is rotating, and we don't know the angle of the rotation axis of the star with respect to the plane of the sky, whether we're seeing the star rotating with the rotation axis in the plane of the sky, or perpendicular to the plane of the sky, or somewhere in between. And you could, it could be a completely different Doppler signature depending upon the inclination that you're looking at. And so, for A stars, for example, which rotate fairly rapidly, you can actually have temperature gradients across the photosphere of the star. And that's not, it's an extreme. You don't really see that for older main sequence star, or for the main sequence stars we primarily study with the Doppler technique. But at the moment, that to me is one of these open questions that kind of can affect different stars differently. And we don't, we can if we have a rotation period photometrically and a V sin I, you can make an estimate of the inclination, or if you have an interferometric radius and a photometric rotation period, you might be able to make an estimate of the inclination on the sky. But how inclination plays a role in stellar activity signatures is something that I'm just curious about generally.
You can pull out the inclination of if you have astroseismology. I don't know if that's where you were going with Annelies.
No, I was going with X and B, but go for it.
Okay. Yeah, but if you have a precise enough astroseismology, you can use that to pull out the stellar inclination by looking at the oscillation modes. And so I believe that's mostly been done with space-based photometry and perhaps for more evolved stars. And I'm not exactly sure what level of precision that we need to do it with radial velocities, but I believe that fundamentally it can be done, and we can get that from RVs, to answer your question, Peter.
There's also, I think it was shown, well, at least I've seen it, but I think it's published, that the behavior of the radial velocities and activity indicators combined for some of during the more active phases of, I think it was alpha and B, showed opposite behavior as what we physically think a spot should show. And it actually turned out that the star is probably inclined, and what we see is the spot not going on the front surface of the star, but on the back surface of the star, which made it rotating the other way around, which made every effect exactly the other way around. And because we saw that, well, I wasn't part of this, because they saw that they could actually put limits on the stellar inclination of the star.
And for I'm sure you know, Peter, but for some of those listening in who may be less familiar, if we have transiting planets, then we can use them to pull out the obliquity or that inclination angle. And if you know that your star differentially rotates, then you can use either the spot modeling in the photometry from that differential rotation, or you can use the spectroscopic transit and try to fit for the differential rotation component there to pull out the stellar inclination directly using essentially your transiting planets to probe that.
So one question that came up a bunch in the Q&A, or one topic, is how we can extend what we've learned about the sun to other kinds of stars. So subgiants are going to behave differently, but I think a lot of people are especially interested in cooler stars, going down to the M dwarfs. So how many of these lessons extend down there, and what do and don't we know about these things, for instance, for fully convective M dwarfs or for any other spectral type?
Heather, you want to take that one?
Yeah, I can take it from perhaps a granulation point of view. So the understanding from sort of that I get from working with the magnetohydrodynamic specialists is that really you can kind of look at the MHD side from the ground up and see how the convection is going to vary as a function of spectral type. So you can tweak the mass and the effective temperature and the surface gravity all together, and really look at, say, okay, now we create a simulation and we validate it on the sun, and if we get the fundamental physics here, then this essentially should scale as long as you have convection operating. Things may get a bit more complicated when you come to things like spots, you know, because you might need to understand the dynamo mechanism that is actually driving those spots. And if you have a fully convective star versus a star with no convective envelope at all, the fundamentals driving that is probably a bit different. But we can know from sort of ground principles what we would expect to scale, and especially for the oscillations as well. I mean, Bill Chaplin and some others have done wonderful work in the astroseismic side of things, and showing how we can use these sort of scaling relations to go from the sun and to other types of stars. And when you have loads of stars, that really helps you get a handle on things. But I think, as I mentioned before, we definitely want to make sure we are empirically validating things. So one particular way that I mentioned a couple of times is to validate it on the sun. And then once you come up with some model and you apply it to other stars, you can see if it explains the data. And then on top of that, you could possibly, if you're lucky enough to find ideal systems that have transiting planets, you can use them to probe and resolve the star a bit more and push that another step further. So I think the answer is you probably translate pretty well from the sun to stars with a convective envelope, and you probably do reasonably well even when they're fully convective, but there's still more to learn. I mean, we still have more to learn for the sun.
One question that came up is what we know about fully convective stars' magnetic fields, and whether how we understand if they're generated the same way as in the sun, and if not, what are the implications perhaps for spots?
Well, one thing that I will say is that there's not even agreement for the sun. The most maybe commonly accepted dynamo mechanism is this sort of alpha omega dynamo, where you have the center of the star rotating as a solid body and the envelope being differentially rotating. And you have these poloidal fields that then get wrapped up and turned into toroidal fields. And then they go ahead and they travel upwards in the convective envelope because of the convective motions pushing them up, as well as magnetic buoyancy. And that's why you get these spots with sort of different polarities from that magnetic loop coming up. But still, there are other mechanisms there are other dynamo theories to explain things. And some of them are saying that there's local dynamos just in the convective envelope itself. And that's what's driving some of the magnetic interplay here. So I think the answer is we don't know. I'm sure that some dynamists will have their favorite theory and their favorite explanation. And I don't know if anyone here is familiar with fully convective M dwarfs and can add to what they think might be happening there.
Your understanding is basically the same as mine. Oh, Annalise?
No, I was just, because there was a silence, I was just going to mention that the polarimetric community are really trying really hard to get measurements of these magnetic field structures around cool dwarfs. So the whole Be Cool organization, they collaborators. Yeah, the whole they have exquisite papers where they really try to map what the magnetic structure and all the lines and actually do for other types of stars other than the sun. They have their famous confusograms with all the information in one plot. But I think they're helping by actually making observations of the magnetic field structures of other type stars.
Yeah, I'll add to that. The polarimetry community is another technique. If you have enough polarization to detect differences in polarization, to isolate activity signals as well. Specifically for M dwarfs that are fully convective or even more convective than a G-type star in terms of the amount of the star of atmosphere that's convective, we know that calcium H and K activity indicators don't work as well as they do for G-type stars. And so there's some groups that rely on activity indicators will use the H-alpha as a different activity indicator for looking at M dwarf radial velocities due to activity. And I think generally speaking, in an ideal world, getting back to the physics, you'd like to have indicators at a range of scale heights in the atmosphere, because what's going on in the chromosphere is not the same thing that's going on in the photosphere. And Annalise, you've shown that with your activity indicator time lags.
There's a couple of questions here about activity studies with RV. One asks if we know of any examples of radial velocities being negatively correlated, redshifts being negatively correlated with activity levels. Everything we saw showed radial velocities getting larger with activity, but does that ever go the other way?
I'm not sure if this is going to answer the question, but at some stage, if you have enough magnetic field, then you are going to suppress the convection enough that you essentially just have less activity. So, or you could think of it like if you had spots everywhere, then you're going to have sort of less activity. So there are some cases when it's like that. And I guess it depends what you mean by the sign of your correlation. For example, when the sun is in its magnetic activity and it's most active, it's actually brightest. And so you would think because there's more sunspots that you should be darker, but actually it's also the contribution of the plage as well. So that's an example of sort of the correlation perhaps going the other way.
And that correlation is different for cooler stars, isn't that right? I think it goes the other way for much cooler stars, but I may misremember.
It will go it might be the case for cooler stars, but I'm thinking there's also a transition between whether you're faculae/plage dominated versus spot dominated. And if you're spot dominated, then being more magnetic is going to be darker. But if you're plage dominated, then it's going to be brighter.
Have there been studies on activity in binaries? I love binary stars because they hold everything constant except the mass, especially if they're widely separated, and you can get precise Doppler measurements of both components of the binary. So what have binaries taught us about RV jitter?
I think an unfortunate fact is that for the most part, RV surveys avoid binary stars due to concerns that if they're close on the sky from our point of view, then you're going to have contamination when trying to observe one star or the other. There are cases where the stars are well enough separated that you can observe both of them, and then you can actually see both the RV variations due to the two stars on one another. And if you model that out, you can then look for, much smaller variations due to planets around those stars. But as far as I know, it has not been a super focused stellar set that we go after, just because there are additional hurdles that have to come between observing them, how you observe them, and then reducing the data. It's not the same as the binary star question, but Megan Bedell has done some nice work on RVs of solar twins. And so picking stars that are very close in terms of stellar parameters to the sun, with the idea that they should, again, hopefully share other characteristics, though we know that's not always the case. But yeah, I think, binary stars, moving forward, I think they're definitely an interesting focus case, but I don't know of a ton of work that's looked at them and their activity in detail. Maybe other folks do.
I think Alpha Cyn b is one of the more famous examples, which is both in a binary and has been terribly active. And it was the star that, well, it used to have a planet, now it doesn't. But you can track the magnetic cycle through it quite well, and that relates with the calcium index, whilst the effect of the binary is separated from that. And then still trying to find a planet in all that mess is obviously very hard, but there's lots of data on Alpha Cyn b, which is both binary and a relatively active star. It was the focus of Andrew Thompson's work that looked at the specific lines. They very purposefully chose Alpha Cyn b for their study.
Yeah, that's an excellent point. And that's what Xavier's work on the line-by-line stuff is focused on as well. So yeah, for sure that is a good example of a binary star.
I think it's an example where the binary is mostly separated enough that they don't really interact so much. So we can kind of treat them as separately. Is that correct?
Yes.
I think so, yes.
And the one thing I believe is correct is if the binary stars are close enough to one another, then they can spin each other up. And if you spin each other up, then when you are rotating faster, then you tend to have more star spot activity as well. So those sort of things were probably going to be a double whammy. If you spin too fast, then you lose RV content information as well. So there's a few complications that go into there if you get your binary too close and interacting.
So an anonymous attendee asks to extend the conversation to clusters, which is not something we've talked much about, but there's a lot of RV work in clusters. What has that told us about RV jitter? Because all those stars have the same age and composition.
I don't know. I know of people working on clusters. I think the Italian group with Luca Malavolta and others are specifically working.
Yeah, I think in general, the problem with clusters is that the stars in them tend to be pretty young. And so we learn a lot about very active stars from clusters. But it's hard to find a cluster with really old, quiet stars of the kind we think about for extremely precise radial velocities.
Yeah, because I was just going to add to that, talking about bringing in the age and the activity. So there was some discussion about sort of how do we target less active stars, and whether we should use the RHK or not. But we know that the S-index or RHK, whatever variation you want to look at, can vary over an activity cycle. You can go from quiet to very active. But one thing that we can pretty much say is going to always cause trouble is the age, is if they are young and they are rapidly rotating. So those would be a safer bet if you wanted to fine tune your target list, is to avoid really rapid rotators and those really young ones, rather than perhaps the other activity indicators.
We have a question online asking about planet-star interactions and whether the planets themselves might induce a activity signal, which I would always be worried about, because if the planet is causing the activity, then we say, oh, that signal's correlated with activity. It must not be a planet, when in fact it's totally a planet. It's just coming along with activity. So that's kind of the opposite of jitter, where the planet's causing it. People have any opinions on that? Yes,
I think
and
it's
can
a
hot
great
Jupiter's excite
question.
activity?
Yeah. Sorry, I dropped out earlier. I think my tablet is overheating from the interesting discussion. But I think it's a great question. I think the group of Helene Pidotto is trying to answer part of what's happening there. But as you say, it's very hard right now to make that distinction. Is it an activity signal, or is it the planet causing the activity? And we really need to know more first. Because people are starting to become, rightfully so, very wary of calling something a planet in radial velocity data, as they should. But I think it first needs to come from the stellar physics and the more simulation kind of side, combined with observations, before we can, use it in our radial velocity search.
Paul Robertson comments that activity radial velocity anti-correlations are observed in several M dwarfs, which gives me a segue to ask Peter and Colin about the particular challenges of activity in the infrared and lower mass stars, or perhaps younger stars. Can we, use all the same tricks that we use in the optical there?
Peter, I'll let you lead off.
Oh, yeah, that's good. All right. Okay. Well, to first order, and it's not always the case, the activity amplitude for stellar activity decreases towards the near infrared as 1 over lambda, but that's just an approximation, assuming you're spot dominated, and that's not always the case. Certainly for younger stars, that's more likely to be the case, and that has been observed with near infrared Doppler spectrometers. This relates to a question on a Q&A about whether or not RV variations caused by tellurics can vary activity-induced RV variations. And Sharon Wang gave a great talk on that yesterday. And then Colin, you gave a talk. I missed your talk, Colin, on that earlier today. Apologies. And in the near infrared, you might argue that the effects of RVs from tellurics are somewhere on the order of a meter per second. We don't actually know where that level is at this point in time, the effects of tellurics. So yes, that's definitely a possibility in near infrared, that tellurics could limit our ability to assess activity. But I think in general, the leverage in using the near infrared for activity diagnostics, number one, there have been some activity diagnostics. I think Barbara Rojas Ayala has done some kind of indicator stuff. I'm not entirely familiar with that work though, but I don't think there's emerged like a set of good near infrared lines that are activity sensitive in the near infrared. I don't think anyone's actually done that yet, nor do I necessarily know if that's the best place for, say, G-type stars, but it might be for M-type stars where they put out most of their bolometric flux in the near infrared, whereas G-type stars put out most of their bolometric flux in the visible. So I think it's a spectral type dependent thing. Colin?
Yeah, I agree with all that. I think we've seen some beautiful plots from Carmenes showing, even earlier today, showing the correlation between wavelength and derived velocity. And I think that reminds us that when we think about activity, for some of these low mass stars, it's a fundamentally different beast. There are some famous low mass stars that, their line emission in certain lines can change by factors of like thousands, right? They're extremely, extremely active. Now we might just avoid some of these famous flare stars, but these are some of our nearest neighbors, and it would be fantastic to figure out how to sort of work around this presumably chromospheric emission and detect changes in the center of mass. But yeah, activity can mean a totally different thing for a low mass star.
Colin's talk was also great, just so you know, Peter.
Good thing this is being recorded. I can go back and watch it later. Thank you to the host for doing that.
Jason,
I think you're muted.
Of course I am. I was going to say I'm not totally up on this, but I think in the near infrared, the helium 10830 line might be valuable for some of the more active stars as a chromospheric activity indicator.
You can
All
call
right.
that near infrared, but I still think of that kind of close to the visible.
You call it the near optical?
Yeah, yeah. I'm a bit biased out at 2.4 microns.
Okay. Okay, great. Well, that's about all the time we have for this panel. I want to thank all 5 of you. That was a really great discussion. I'm glad we got to a lot of the attendee questions for that.